Okay, then we shall begin. I hope everyone's doing well. It's August, best month of the year. Maybe. All right. Okay, so you guys should have seen your exam scores posted online. And again, if you want to take a look at your exam, you are more than welcome to do so during office hours. And but if you want to see it next week, I just ask that you send me an email so I can pull your exam from the stack rather than having to bring the whole stack to school. Okay, so let me just recap where we are in the course and what we will. Whoa, something's going on here. Okay. Okay, so, all right. Do we remember why we bother studying statistics? What was, what did we say? Yeah, Micah.
Study a population of people.
A population of people, okay, and
study a small population.
Okay, a part of that population, yeah. What?
Understand the world around us better.
Okay, to help us understand the world around us. Yes. So what statistics allows us to do is it allows us to just study a sample, which will then give us insight about a population. Okay, so we study a sample, okay, which is a small group, and this allows us to make information, or allows us to make conclusions about the population being a group that is too large to observe directly. Okay, so that is why we study statistics. And so far in this class, we have covered two parts. Okay, the first was on descriptive statistics. Okay. So under descriptive statistics, you learned things like finding the mean, the median, the standard deviation, the IQR, or we even talked about descriptive statistics for two variables. And what do we have for that? We had the correlation when we talked about two variables. Okay. So that was descriptive statistics, and then we also learned about probability. And when we learned about probability, we learned the rules of probability, but we also learned about the normal distribution and the binomial distribution. So that was our exposure to probability. Okay. So this is what we've done so far, and this is kind of what our midterm exam covered. Okay, there was a bunch of stuff, but broadly we could divide kind of chapters. I would say chapters 1 through 4 were on descriptive statistics, and chapters 5 and 6 were on probability. Okay. And so today we are merging these two together. And this is where we start doing statistical inference. Okay. And so this is chapter 7. Whoops. And the rest of our class will look at chapters 7, 8, and 9. Okay, so we're going to cover chapters 8 and chapters 9, and then just very briefly a few select subtopics from chapter 12, but the bulk of the remaining part of class will be coming from chapters 7, 8, and 9. Okay, and this is where we bring together. So I'll say chapters 7 through 9 and 12, bringing together the concept of descriptive statistics and probability. Okay, and so the idea behind this, again, is the idea that we study a sample and then we're going to make conclusions about the population. Okay? So we're going to just go over some terminology that we've probably seen already, but it is good to go over them again. So let's it's August 4th. Okay. All right, so some terminology again. So the population. Do you guys remember what the population is?
Everyone?
Okay, this is everyone relevant to what? Yeah, everyone relevant to our research question. Everyone or everything relevant to our research question. Okay. The sample is what? Yeah, a portion that we can observe, a portion taken from the population that we can observe. Okay, so the population has parameters. So a parameter is a property or characteristic of our population. Okay. And usually our studies are done so we can learn about this parameter. Okay, we want to learn On the other hand, so the parameter goes with the population, and what goes with a sample? We have a statistic. So the statistic goes with the sample. So this is kind of the parallel characteristic or property from our sample. And the statistics, sometimes we call these estimators. They're also called estimators because they kind of provide a estimate of the parameter. Okay? Also called estimators because they can act as an estimate of the parameter. So inference is all about taking what we've learned from our statistic and saying something about our population parameter. Okay, so again, population and parameter. So I'll let you guys get that all copied down. Okay. All right, and so in order for our conclusions from the sample to be valid about the population, what did we say has to be true about the sample? Yeah.
It has to be randomly taken from the population?
Yeah, well, okay, so it doesn't necessarily have to be random, but you're getting at the idea in that it has to be representative, okay? Our sample has to be representative of the population, and one way to get a representative sample is through random sampling, okay? So our samples need to be representative of the population. Okay, so I know I've covered a lot of this before, but it's very important and it's especially relevant to the stuff we're doing now. So we're doing this again. So our samples need to be representative of the population. Okay. One way to get representative samples is through random sampling. Okay. If our sample is not representative, it is considered to be biased. Okay, and there's different things that can cause bias, but I'll leave it to you in your reading to read about bias. Okay, so anyway, random sampling should give us a representative sample. It's not perfect, but it should give us a representative sample. Okay, so let's do a simple kind of thought experiment here. Okay. Imagine I've got this is a giant bathtub full of are you familiar with Reese's Pieces candies?
Yeah.
Okay, so they look like M&Ms, but they have peanut butter inside. So sorry to you with peanut allergies, but Reese's Pieces candies, and they come in 3 colors. Okay, we've got orange, yellow, and brown. Okay, and so let's say you fill up your entire bathtub with Reese's Pieces candies. Okay, so there's like hundreds of pounds of candy in here. Okay, so this is a bathtub full of Reese's Pieces. Okay, this is a bit ridiculous, but just stay with me here. Okay, and so let's say we want to know, and we want to know what percentage of these Reese's Pieces, what percentage are orange? This is a very important question, as you can see. Okay, so this is what we want to do. Okay, now we don't feel like going through the entire bathtub and counting every single piece of candy, because that would be a lot of work. We don't want to do that. Okay, so what we're going to do is we're going to use statistical inference. We're going to stir up the bathtub, make sure everything is nicely mixed, and that way when we draw kind of a handful out of the bathtub, it can be considered to be randomly selected. Okay, so we're going to, so let me just write down what we're doing. Okay, so we do not want to count all the candies. So we will use statistical inference. Okay, so we stir the bathtub. We stir the tub, so this is kind of like randomizing. And then we draw maybe a cup full of candy. This will be our sample. And again, because we stirred the tub, it can be considered a random sample. Okay, and so we're going to count all the candies in our cup, and based on what we see in this cup, we're going to make conclusions about the percentage of candies that are orange in the entire bathtub. Okay? And that is the idea behind statistical inference. Based on what we see in the cup, we will make a conclusion about the bathtub. Does this concept make sense? What's going on here? Okay. So I know this is a silly question, okay? This is a silly scenario with the bathtub, but I think it makes it, you can imagine how this process works, right? We've got a bathtub. We want to know what percentage are orange. So we're going to stir up the tub. We pull out a cup of candies. We're going to count how many are orange in this cup, or we're going to find the percentage that are orange in the cup. And based on that, we're going to try to make conclusions about what the bathtub is like. What percentage in the bathtub is orange, okay? Now so nobody would probably actually do this with Reese's Pieces candies, but this same thought process can be used for maybe questions that we consider important. So, for example, you know, the Republican primary is coming up, right? And there's like 10 candidates. They're going to have a debate soon or whatever. You know, there's like 17 candidates, but only 10 got selected for the debate. But the question is, you know, who's going to win the primary? That's what people really want to know. And so we can kind of think of as the population of voters as kind of the bathtub, but until election day, we're not going to be able to count everybody in the population, right? There's too many people. So news organizations or different organizations do random sampling, trying to look at, maybe they survey 200 people, okay, rather than all millions of voters. And based on what they see from their sample, they're trying to figure out who is leading, okay, who's going to win the primary, or who's going to win the election. So when they talk about who's leading in the polls, this is essentially what they're doing. They're taking a cup or a small sample of people. Based on this sample, they're trying to make conclusions about the general population. Okay? But with candies, we can kind of, imagine this, and the random selection process for people is complicated, but when it's a bathtub of candies, it's easy. Okay? But the same kind of thought process applies there as well. Okay? Okay, so let's say you take your cup has 50 pieces of candy. Okay, and let's say 18 of them are orange. Okay, so your sample proportion of orange candies is what? It's going to be 18 divided by 50, or 0.36 orange. Is that all right? Okay, and so the symbol we use for our sample proportion is p hat, okay? We're going to use p for a lot of things, and to indicate that this is the sample proportion, we put this little kind of roof over it. It's called a hat, and this indicates that it comes from a sample. And so the question is, what does this say about the population proportion? Okay, and the population proportion uses the symbol P. Okay, so P would be the proportion in the population that's orange. So that would be the answer if we counted up every single piece of candy in the bathtub and we found out how many are orange. Okay? So that's the population proportion. So population proportion is, the proportion that's orange in the entire bathtub. To disable this. Okay. Is that okay? So if p hat is 0.36, what do you think p is? Can we say anything? Well, the answer is p is probably close to 0.36, but not necessarily exactly the same. For example, I don't know, 20% of people surveyed support this candidate. Does that mean 20% in the entire population support the candidate? No, not necessarily, okay? But probably something around there support that candidate, okay? Okay, so to get an idea of what p hat can say about p, we're going to do kind of a little experiment or a demonstration. And the idea is I'm going to set up kind of this scenario. We can simulate this bathtub scenario. And we're going to repeatedly draw cups of 50 candies out of it. Okay? And we can see how close does our cup get to the actual population proportion. So for example, I can say I've counted all the candies in the entire bathtub, and I know that exactly 32% are orange. Okay? And if I say I know exactly 32% are orange, I can see how often will my cups end up being 36%, or how often will my cup end up being 32%, or things like that. Okay? And we're going to do this simulation with on the computer here. Okay, so this is called there is what we call the Reese's Pieces applet. Yeah, this is what we want. We want the. All right, can you guys see this? So this is kind of our giant candy tub. Okay, and so so what I'm saying is that I'm saying in this giant tub, 32% are orange. I'm going to take out 50 candies at a time. Okay, and we're going to calculate the proportion that are orange. So we're going to just do this first one. We're going to animate it. Okay, so if they're orange, they get sent over here, and if they're yellow or brown, they get sent over here. And so, oh, okay, so by coincidence, we happen to get 36%, okay? So, you know, we can see here, you know, can I zoom in here? Okay, so, you know, we're not going to do this every single time, but we can count. There's 18 orange pieces. 18 divided by 50 pieces total is 36% orange, okay? And so I'm going to build a dot plot down here, and I put a dot at 0.36. Okay, and I'll do this another time. And so here I get okay, here I got 21 pieces that are orange. Remember, in the bathtub, it's really just 32% orange, okay? But here I got 21, so I got 42% are orange here. And so I put a dot at 42%. Okay? All right, we'll do this one more time, and then we're going to just start accelerating this, just so you don't have to sit through all of this. Okay, and here I got, what is that, 19 orange pieces, so that's 38%. So I get another dot right there. Okay, so I'm going to turn off the animation, and oops, and we see here where I got 32%, 34%, 18%, 36%. So we can see we're getting you know, just several different values of p hat. Okay, and I can do let's see, a bunch of things. So that's let's do 80 samples. So it's going to throw 80 dots onto here. Okay, so it's going to do this very quickly. So here I've done a total of 100 samples, and this is what it looks like so far. Let's do another 100, and this is what we're seeing. So after 400 samples, what do we see? We see very often we get 34% and 32%, and you know, we get values around 30% and around here quite frequently. Occasionally we get 48% orange, or as low as 18% orange, but the values kind of in the middle are much more frequent. Can we see that? Okay, and so I'm going to just keep doing, so there's another 100, and at this point the dots are kind of super close that they're forming almost lines. So let me just do another 500, and let's see what this looks like. Okay, so there's 1,000 samples. Let's do another 1,000 samples. So here's 2,000, 3,000. Okay, so this is what we're seeing. Okay, what does this look like to you? It looks symmetric. Okay, and it actually fits the normal distribution very, very closely. Okay, so that's what we end up seeing. We see when I'm drawing, every single time I'm drawing 50 candies, and every single time I do it, I count how many are orange and I calculate what percentage are orange. So in this case, again, 21 pieces are orange, so that makes it 42% orange. And I have done this via the computer simulation. I've done 5,000 samples of 50 candies, and this is what it looks like. Okay. So all this to say is that kind of the most frequent percentage of orange candies that I get is what? Right around 32%. Okay? So in this bathtub, 32% are orange, and when I do the simulations, I get in my sample 32% quite frequently. But I also get 34% and 30% very frequently, and even 28% and 36% quite frequently. Okay, so values that are close to 32% happen very often. Values that are a little further away from 32% happen less often. That's what we see here. So let me write this down. Okay, so from going back to this question, my p hat is 0.36. What does this say about p? Okay, so from seeing that p hat is 0.36, we can expect p to be somewhat close. Okay, and this is purposely vague, somewhat close, whatever that is, somewhat close to 0.36. Okay? It may be exactly 0.36, but it could also be higher or lower than that. P could be 0.36, but it could also be higher or lower. Okay, so this simulation that we've run here, this is known as a sampling distribution. Okay? All right, so we have run a computer simulation okay, in the simulation we repeatedly take random samples from the tub of size, random samples from the tub. Okay, the samples are all of size n equal to 50. Okay, we know the proportion in the tub P is equal to 0.32. Okay, so there's no hat on this P because it's the population proportion. Okay. We keep track of all the different p-hat values. After 5,000 samples, each of 50 pieces, we get the following distribution. And let me draw this here. So what do we see? P-hat that is close So again, this graph here shows all the different samples. There's technically 5,000 dots here. They're just so close that they merged into lines. It looks like lines. But there's technically 5,000 dots. Each dot represents a different sample of 50 candies. And every time we took a sample of 50 candies, we counted how many are orange and calculated the proportion that are orange. Okay, and what we see is that very often, because the population is 32% orange, very often I get samples that are also close to 32% orange. When I take other samples, though, I get samples that are maybe a little bit higher than 32% or a little bit lower, but generally something around there. Okay? Does that make sense? What do you think would happen if I took samples of, let's say, 200 candies rather than 50 candies? What do you think?
It would be the same.
Do you think it would be the same? So now I'm going to, rather than taking 50 candies, I'm going to take a bigger sample. I'm going to take 200 candies. So maybe I took 1 cup before, now I'm going to take like a quart. Yeah?
It would be closer to being more exact.
Yeah, okay, so let's do the simulation and see what happens, okay? So notice that, you know, with 50 candies, most of the time I'm very close to 32%, but I might end up as high as 48% or as low as like 16%, okay? It doesn't happen very often, but it seems to have happened, you know, a few times, a couple times. After 5,000 attempts, I might have gotten 48% a couple times and 16% a couple times. Okay, this time I'm going to change it. I'm going to do 200 candies, and we'll just start off with 1 sample. And it's so many that it kind of overflows. And here I got 27% orange. Okay, so let's do like 999 more, and let's see what this looks like. Okay, so we're getting kind of like this, and let's do a total of 5,000 samples again. Let's see what happens. So again, the tub is 32% orange. Okay, and so we get, this is what we get. Here, this is samples of size 200. Do you guys understand the difference between this one and this one? The other one? So let me draw this. Okay, so this is what we call the sampling distribution. Of p hat when my sample size was 200. Okay. So what do we notice here? Here, let me just show you the other one. Okay, this was the sampling distribution. Okay, so notice these values here. So rare values, so 0.16 happened, was uncommon, but still happened. Okay, what about, do we see 0.16 over here? No, we don't. Okay, so 0.16 would be something down here. Okay, so 0.16 never happened over here. Okay, and instead, what we see is values around, 0.24 is now a rare occurrence, is pretty rare. What do we see about 0.24 here? 0.24 is pretty frequent here, right? Fairly common, 0.24. Fairly common. So what does this tell us? This tells us that with a larger sample, most of our numbers are even closer to 0.32. Okay, with a larger sample, our p-hats do not stray very far away from the actual value of p. Okay, so keep in mind, p is 0.32 in these examples. Okay, and with larger samples, p-hat does not, quote, stray far away from the true value of p. Yes?
So the more times that you would run to get the samples, would it be the more specific that you're...
It's not that I'm running it more. In both cases, I ran the simulation 5,000 times. What it is, in one simulation, I only took samples of 50 candies. Okay, that's like a handful of candies. And in the other simulation, I'm taking samples of 200 candies. Okay, and what we're seeing is that the sample of 200 gives us a better idea of what the population looks like. Okay, so the population, we still don't know exactly what it is, but well, in our simulation we do. In our simulation, we know that the population is 32% orange. And what we see is that samples of size 50 get pretty close to 32%, but it's not unusual for it to end up being fairly different from 32%, ending up at like 48%. Okay, but when I'm taking samples of 200,
Is it more precise?
it's I'm not straying from 32% very much. I never saw a sample of 48%, and you know, events of getting like 39% becomes pretty rare, whereas with the sample of 50, getting something around 40% was not a rare occurrence. Is that okay? So the sampling distribution tells us how common different values of p hat will be when we randomly select samples from the population. Okay? Tells us the distribution of p hat. Okay? Again, keep in mind the population has proportion p. Okay, and we randomly select samples. We randomly select a sample of size n from the population. Okay, so our random samples will have different values of p hat. Random samples will have different values of p hat. And the sampling distribution tells us how common those different p hat values are. Okay. What we also saw from our simulation is that our sampling distribution of p hat follows the normal distribution. Okay? And it will have these properties. Okay, so this is So learn this. The sampling distribution of p hat follows the normal distribution under certain conditions. Okay. And what did we learn before the midterm? That all normal distributions are defined by two things. A mean and a spread, the standard deviation. Okay, so all normal distributions have a mean and standard deviation. Okay, so the sampling distribution follows the normal distribution under certain circumstances, and the distribution has mean equal to P. What is P?
Population.
The population what?
Proportion.
Proportion, okay? So the mean of this distribution is the population proportion P, and the standard deviation is going to be the square root of P times 1 minus P over N. Okay. We hanging in there? All right, so let's try an example out. Okay, so let's say the bathtub is 32% orange candies. Okay. We will take a random sample of 50 candies. Okay. What is the probability that the sample of 50 candies ends up having, we'll say, 26% orange or less? Okay. Does this question make sense? I'll let you guys write it down first. So, again, keep in mind the bathtub, I guess we've counted everything in the bathtub. We know the bathtub is exactly 32% orange candies. I'm going to take a random sample of 50 candies out of the bathtub. So I stir it up, and I take a random sample of 50 candies. I count them up. I'm not necessarily going to get 32% orange candy. Okay? I might get something lower than that. And I want to know, when I take a random sample of 50 pieces, what's the probability that only 26% of them are orange? 26% or something less. That's what I want to know. Okay? So to answer this, let's try this out. Okay? So we know P hat comes from the normal distribution. Okay, and the mean is going to be what? P, and the standard deviation is going to be the square root of P times 1 minus P over N. Okay, so what is my mean? So when I look at the problem, I see that the mean, P, is equal to 0.32. So my mean is equal to 0.32, right? So my problem says that the population proportion is 32%. What is my sample size? N is 50, right? So my standard deviation is 0.32 times 1 minus 0.32 divided by 50. Let me pull out my calculator. So I get point, so I'm going to do square root of 0.32 times 1 minus 0.32 divided by 50, close parentheses, I get 0.06596. Oh, 5969. Oh, okay. So I'm going to just round up to 0660. Or no, 06597. Okay. So that's my standard deviation. And then I want to know what's the probability of getting 26% or less. So now I have a normal distribution. The mean is at 0.32, and I want to know 0.26% or less. So how do I get this area? What do I do? What's my step? Huh? I subtract? Yeah, so I'm going to find a z-score, right? So how do I do that? I subtract 0.26 minus 0.32, and I divide by 0.06597. .26 minus 0.32 divided by 0.06597. I get negative 0.91. Z-score is negative 0.91. Now what do I do? Yeah, I go to my Z table. So I look up negative 0.91 and I get 0.1814. So from table, the area to the left is 0.1814. So my answer here is 0.1814. Does that make sense? All right, so let's give you guys another similar problem, okay? And I'll let you guys try this out. Are we feeling okay about this? Okay, so now let's say somebody wants to know about the yellow pieces of candy. Okay, so let's say the tub is 36% yellow candy. Okay, and we will take a random sample of 120 pieces of candy. Okay, what is the probability that this sample is over 40 42% yellow. Okay, so again, just some helpful tips. You're going to have a normal distribution with mean equal to p and standard deviation equal to the square root of p times 1 minus p over n. Okay, so see if you can answer this question. Remember, look, pay attention, it says over 42%. So I'll give you guys a few minutes to work on that. I'm going to pause the video if you're watching on YouTube. Okay, so I was walking around and it looks like a lot of you guys are doing great, and that's very encouraging. So let's take a look. Okay, so here the tub is 36%, so we're going to say our mean is p equal to 0.36, and we are taking samples of 120, n is equal to 120, so our standard deviation is going to be the square root of 0.36 times 1 minus 0.36 over 120. So I can just do 0.36 times parentheses 1 minus 0.36, close parentheses, divided by 120. That goes inside my square root, so don't forget to take the square root. And so my standard deviation, I get 0.04382, okay? Okay, and so now, if I draw my little picture, I've got 0.36 in the middle here, and I'm asking for, what is it, 0.42 or more, okay? So I think, you know, a lot of us, maybe we prefer not to draw pictures, but I think the picture always helps me remember, do I want the area to the left or the area to the right, okay? So I'm going to go z is equal to 0.42 minus 0.36 divided by 0.04382. So on top I do 0.42 minus 0.36, close off the parentheses, and then so I do a little shortcut. I just throw in answer here, okay, because I have 0.0438117 still in my screen here, so I can just do that, and I get 1.369. So I'm going to just round that off to 1.37. So my z-score ends up being 1.37. I look this up in the z-table. I go to 1.37, and I get the number 0.9147. So here I get the area to the left of 1.37 is 0.9147. That's going to be this area over here. But the question says, what's the probability that the sample is over 42%? So that answer is going to be 1 minus 0.9147. And I get 0.0853. Okay, and so that will be my answer, 0.0853. Okay. So this is a sampling distribution problem, okay? And of course it's not always going to be bathtubs and Reese's Pieces candies, but it could just be anything where you've got a population where a certain proportion has some quality, and we're randomly selecting a sample from that population. Okay. All right, why don't we take a 15-minute break here, and then we'll finish out Chapter 7.